Okay, so let's start. So some of you have been talking with me about projects. I want to throw a few additional ideas, which sort of your way. So there's a fair bit of energy-related data that you can access, and in particular, there are two very good sources of data. So I'm going to put them out here. One is, and this is actually a pretty interesting website called data.gov, and where federal government puts all sort of data. The particular link that I have kind of put up out here, thanks to Bharat, uh, is hourly information on U.S. electricity supply, demand, and flows which exist out there. Um, so a lot of this kind of data is available in a single place. So a project here could be along the lines of, could you develop methods by which you can predict the or look at some interesting insights into the data. So for example, you could look at uh, could you predict things like what might happen in major events? Super Bowl is coming. Usually, these kind of events happen where there are very significant power spikes and stuff like that, and they sort of carry some ramification also for the utilities, because, like, even trivial things like when the Super Bowl halftime happens and everyone goes and opens the fridge and all, and suddenly there is a spike. Okay, so there are all sort of these interesting events happen. So being able to predict those, so this kind of data is kind of interesting in that regard. Another data source which exists is from CMU, and this is with for EVs. And here, potentially the kind of things that you could do is, for example, try to estimate what is the energy usage which is happening. So those kind of things. Another thing you could examine, I guess, with the original data set is, or even doing your own measurements, how energy proportional things are. So, like, for example, at your own home, what kind of baseline power that you are seeing. Now, this would require you to have some sort of access to the electric meter so that you can put some measurement capability out there, or using these kind of data set, examining how far off are we from that ideal of energy proportionality. So just want to throw these out, that if you look around on the web, there are existing data sources that can be tremendously beneficial. So people collect these data. Another type of data set, again from a variety of sources, is has to do with how do you estimate things in terms of energy consumption at the home. So we'll see it later in the course, but one of the things which people have worried a lot about is, can we measure in a disaggregated manner what is happening by way of energy consumption in a home. By disaggregated manner, what I mean is that could I break it down into different usages within the home? So normally, if you think of energy usage at home, you get a monthly bill or a bi-monthly bill, and that's the granularity at which you get to know what's happening. It turns out that being able to, so two parts. One, kind of a real timeliness. That is, if we can measure what is happening now, hopefully we can, you can provide intervention and influence people's habits. So, like, for example, in cars and all, you kind of, in some cars you see now instantaneous fuel consumption and all, and the idea is that feedback hopefully kind of makes you think and not accelerate hard and all. But the other part also is breaking it down. If I simply were to tell you that, oh, your home consumes so much right now, but not break it down into, maybe it was person A versus person B, or what kind of activity. So that kind of insight. So one way you can imagine doing this thing is that every endpoint that consumes some sort of energy, you put a sensor there. But that gets rather expensive very rapidly. So an alternative approach from 1990s, original proposal in 1990s, is that if I were to measure the voltage and or current at the central meter, so as appliances come and go, the current waveform will change or voltage will see spikes. And by using machine learning and models, you can begin to separate them out. So each appliance, for example, has kind of some sort of a unique signature. They will overlap in time, but you can have imagine that being able to separate them out. So one extreme, dense sensing, other extreme, single point sensor. You can do the same game with voltage, because every time you turn on an appliance, there is some sort of a signature on the voltage that happens, some sort of voltage noise, if you may. So again, you can examine those. So there are data sets also available for these kind of things, and one of the area where people have done a fair bit of examination is that techniques which help you non-intrusively figure out what is happening inside a home by way of power consumption. So that area is kind of just generally one where there's a fair bit of data available. Closely related to it are other facets. So when people talk about energy consumption in a building or at a home, equally important also is what the occupancy related characteristics are. So being able to know something about the occupancy in the home. So just like non-intrusive sensing of energy consumption, there is also non-intrusive sensing of who may be consuming, like the individuals, where they are. That knowledge can be used to, in turn, power manage the home. For example, trivial ones being lights being turned off when motion sensor doesn't see motion, but there are a lot more sophisticated stuff, like for example, HVACs can be HVAC for a zone in the building can be controlled in a smart manner and all. So sensing occupancy is another one which comes up. One concrete project idea which want to throw out is the following: that these ideas around that our homes or buildings are instrumented with sensors and all, immediately besides kind of the cost part which they run into, there's another aspect which they run into, is that it's very hard to or very burdensome to configure and maintain these kind of systems. In particular one is the configuration. Let's say I deploy sensors in various places, but then I have to laboriously enter which sensor is where, what purpose it is serving. Is it this is a sensor which is monitoring light bulb in my bedroom, or so and so forth. So simplifying that process can be quite useful. So the one concrete project idea I want to throw out is the following. Let's imagine I put a bunch of motion sensors in my home, and I don't tell you where they are. Motion sensors and door window sensors. Okay, I don't tell you where they are, but I give you all the traces from them. Okay, with timestamps. Can you figure out where those sensors are, what purpose they are serving? For example, in a smart home setting, I might want to have things like, the light within the like if I'm not at home, something should not happen. Like don't if oven is running, oven is on and I'm not at home, that's unsafe. Or fridge door is left open, stuff like that. But I don't want to go through the pain of laboriously annotating zillions of sensors and what do they correspond to. So just from the traces alone, what can you infer about the purpose of those sensors? Just to make it a little bit more like what the intuition is, you might imagine that identifying the front door sensor should be possible, because typically it would be the first event in a series of events which happen after a long gap, or it would be the culminating event in a series of events which happens when I leave the home. Likewise, the order in which events happen at different sensors say something about their deployment layout. Okay, the last event that happens prior to silence at night probably correspond to something in bedroom, and so forth. So kind of the idea would be could you begin to attach some meaning to these sensor traces without actually the user burdening the user with this, or maybe burdening the user with something very minimal, like how many rooms do you have in the home, or what's your home address, and then just use Zillow.com to learn how many bathrooms and bedrooms I have, and then figure out which sensor is where. Okay, So just wanted to bring that out that, I mean, in this sensor instrumented world, a immediate bottleneck people face is that this problem of attaching meaning to sensor data. So maybe I'm kind of defining a project in this manner, that bunch of these sensors, limit ourselves to motion and door window sensors, give you my home address, nothing else. You figure out which sensor was where. Okay, and then we can attach some richer form of sensors, perhaps there's something about sound or stuff like that, but no other sort of data is given to you. Okay, so that's an example so think as you think about stuff, think about these ancillary issues that come in the way of making things energy efficient. And I think when it comes to sensing, I mean, this is one aspect. So let's see, in conversation with various groups, other ideas which have sort of popped up and which are reasonable spaces for project ideas. Nowadays, sort of machine learning of various forms on edge devices is getting a lot of attention. By edge devices, I mean tinier devices, your mobile, smartphone, embedded devices. So looking then at from an energy perspective, because these computations tend to be energy expensive, particularly training. So not simply classification, but actually being able to train. So there are different directions one could take out there. One is you can examine, well, one is simply how about creating a very low power, very efficient embedded machine learning library for, let's say, the embed platform or some other edge device, some other mobile wearable, something like that. Okay, but highly optimized for energy. And the way you optimize it for energy is by exploiting multiple cores. If there's a GPU, perhaps you exploit that, but make it general purpose enough that people can kind of use it, customize it for their particular application. Being able to make so that would be one type of stuff. The other would be to optimize. Another idea which came up in conversation was to make use of machine learning itself in the process of power management. So power management, which we'll see actually in today's lecture, fundamentally boils down to when should I shut down a system, when should I wake it up. It's a prediction problem. And you make use of history and known characteristics of your system to kind of decide that. So you could possibly take a look at different information that your system has. Let's say you are doing it for your mobile phone. So you have access to operating system state, you have access to hardware state, you perhaps have access to some user activity kind of stuff, and you use that to decide how to power manage things. Even I mean, you could do it in a variety of contexts. Like for example, one of the projects some years ago in this course, it had looked into sort of managing in multi-screen settings or with a desktop display, can I automatically turn on off my computers and other resources based upon what I'm doing. You see counterparts of these things in HVAC management and all. Just generally, if I'm not using a resource, it should shut down. So if you know that I'm not using the resource, you could make use of that. Within a computer, when the compute OS sees there is nothing to do, then it has to make a decision: should it shut itself down, should it shut the hardware down, or should it keep up because something will happen pretty soon. Knowing the history perhaps can help you predict that. So so traditionally these things have been done using kind of rules that humans put in and all, or some very simple thresholds and all. One of the things which is happening in recent sort of years is people have begun to see, can we make use of machine learning to make use of these kind of predictions. So you throw data and your goal basically is, given the state, should I shut down? Yes, no. And you basically ask, you have trained a model of some form which will basically give that answer to you. Okay, let's see what else came up. There's also opportunities if in optimizing different types of sensor data collection and sensor information. particularly for wearables. So medical space is one where people are trying to measure all sort of stuff, particularly things related to motion, things related to physiological signals like heart rate and all. So in many of these things, there are some interesting sort of possibilities for optimized implementation of, let's say, heart rate variability, which is you take the underlying cardiac signal, which would be either ECG or the way your smartwatches do it using what's called PPG, pulse plethysmography, I think. Use that to get heart rate variability, which is a good indicator of one's fitness, stress level, a whole bunch of other stuff, as opposed to simply heart rate. Heart rate is easy. Heart rate variability requires a deeper computation. So there's a fair bit of work going on where people try to do these things at the chip level, that is, make the hardware lower power, but you can also approach it from the perspective of optimizing sampling and optimizing processing, and there's a lot of headroom available out there. So anyway, these are some additional ideas, and again, these kind of data which is out there on the web are also potential directions. I'm perfectly fine with projects which pick data sets and provide some deeper insights from that data. That's perfectly fine. Not everything has to be hardware software. Yeah.
Can you show your previous one, the data.government? This is the government daily.
Yeah, so firstly, so if you go to data.gov/energy, data.gov is a general data website of federal government, okay? And on what they have done is they have provided all sort of stuff, including there is an American Energy Data Challenge. So you might want to look here for possible ideas and all also, okay? But point is there's a whole bunch of data that's available. Another one that you would find actually very useful website is Pecan Street. Let me see if I can locate it. Yeah, this one, Pecan Street. It's a University of Texas Austin initiative, and they provide all sort of data sets from bunch of homes and all they have collected about EV charging, solar energy, stuff like that. So you have to kind of sign up, and then they release the data to you. But so this is another kind of mother lode of energy related data that you can kind of find. When it comes to mobile side of things and all, there are websites such as there is, if you Google for data sets and all, you will find that there are various universities which are maintaining energy traces and things like that. So you would be able to locate those. So, but for home type stuff and all, I guess, and car, I think these are some interesting sort of websites, lots of data. Browse through these things to get some idea. I think the energy challenge that data.gov is talking about might be an interesting one to explore. The car EV related data sets are kind of interesting as well. So yeah, so this is some stuff out there. You could even consider doing kind of some sort of a web-based tool for a interesting way of looking at these data. That's perfectly fine as well. So sort of marry the data with some analysis or visualization tools and expose the data that way. Also, just my lab is instrumented with the electric panel in my lab is instrumented with sensors, which give you essentially power consumption for every circuit, and there is a nice little API through which you can access them. So that could also be potentially a source of some interesting project. For example, it could even be some sort of providing some sort of insight about what is happening in the lab, maybe perhaps some way of allocating or creating a energy report for the lab, or doing other type of things like what are the people in the lab, who was there in the lab, perhaps a personalized energy report, that those, 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 those kind of things. But just wanted to mention that I also have similar energy data from my house, which I'm perfectly fine exposing. It's like a fairly fine grained. So these are live data sets, and obviously the sensor part which I described, motion sensors. If you can attach semantics to to uh, a bunch of sensors in a home with minimal information, I think that's actually would be a pretty cool publishable type paper. So I don't know whether, I mean, what the success would be in the sense of how much you can infer, but I have seen Microsoft work where using motion sensor triggers, they attempted to figure out the floor plan of a home. So I think it's doable. Yeah. But anyway, any questions? Any questions on this? So again, come and talk to me. I think many of you have spoken with me, but let's keep the conversation going. And again, be open to data-oriented kind of projects as well. Not everything has to be implement software or implement hardware. Okay, so back to the lecture. So what we saw last time was that one.
I wanted to go back and watch the lectures for lecture 3 and 4. Are those available?
I uploaded 2 of the YouTubes today, and I think the only one I'm missing right now is yes, just Monday's lecture.
Okay.
So last week's 2 lecture are there now, or should be there. Okay, yeah, okay. So Bharat's lecture and my Monday lecture from last week are there. Okay. So so on this one, so we looked at. To recap, we kind of looked at that how you can trade off. You can leverage the fact that voltage there's a very strong dependence V to the power 2 or higher on what is happening to the power, and you leverage that by making use of architectural techniques to compensate for the loss of performance. So essentially, it becomes a same performance or same throughput rather, and a trade-off between area and power, and usually associated with a latency penalty as well, but I kind of made the case that latency was acceptable in many cases. And then we kind of talked about that if one were to start taking a runtime perspective, then really what you have are 2 choices. One is that is a system up and running or is it shut down, and these kind of techniques are called as dynamic power management. And then the other knob that you have is while I'm running, what kind of performance level am I running at? Okay, so one way of thinking about systems is that they give you a bunch of states with different level of power, performance, and functionality. Okay, what are they capable of doing? Usually in these systems, there will be a bunch of states where functionality is the same, as in it's capable of running my program, but the performance and power numbers change, and usually they correspond to, for example, different frequency voltage settings. And then there will be a bunch of states where functionality is gradually crippled more and more, and you gain in power. So for example, it could be maybe certain processor cores are shut down. It could be that I shut down the floating point unit, maybe the radio is shut down, stuff like that. So the increasingly crippled functionality and the accordingly kind of time to kind of restore the state back to a running one. One of the things also is, do I retain the state? Like for example, if I power off the system, then the memory contents are lost. If I want to preserve them, then I have to save them. So so there's a cost of saving and restore. So these are 2 very broad sort of things that you imagine, and in fact, you can think of that every component of the system would have the same thing. I can perhaps have the radio offer me these different states, shutdown versus active, and while active, different rates at which, for example, it can operate at. So what it means when we're trying to do these things, there, as I mentioned last time, there has to be some notion of some aspect of performance and functionality that we are seeking to maintain. Because if you don't have a constraint on that, then of course the best thing is I do nothing, and that's the least power system that you can have. So the type of performance constraints take different forms. It could be tasks with deadline must be completed on time. So this is some sort of a real-time system, and we are saying I want to minimize the power, but we want to make sure that the deadlines are not missed. Um, it could also the constraint may be in terms of throughput. I have a search engine, a database engine, a signal processing server, and I want to just make sure that I'm able to process the incoming tasks at the same rate as I was before, while optimizing for power. So for online kind of systems, this often makes great sense for servers and also for things where you have streaming data. Uh, Another aspect which comes up as you kind of do that power management is that somehow we need to be able to keep track of any changes in the demand on the system that may be happening. It's very easy to design a low power system if I have a completely static kind of a situation. It's kind of hardware design at that stage. But most sort of software systems tend to have changing workloads, things like that. So somehow you need to be responsive to that. And again, there would be additional constraints on that might arise in the process. So we are seeking. So our goal now is we are seeking to optimize something about energy or power, but we also have to take into account some of these constraints that might occur. So if you kind of think about it in a abstract manner, what might a solution for this look like? So one of the things is that for the system to make some judicious decision on power management, there has to be some sort of a model through which the system knows where the power is coming from, how much energy is available, how is the energy being consumed, so that then it can kind of make these decisions. And it may be implicit, but it has to be there. And we kind of saw models of both consumption of energy and production of energy earlier. Uh, System must also have some mechanism by which the performance requirements of the tasks can be acquired by the power management unit. What I mean by that is that what the constraints are. There has to be some way of doing that, because if the task doesn't, if there is no implicit or explicit constraint, then we are back to an unconstrained optimization problem, and the answer to which would be don't do anything. So what this translates into is that if it's a network or if it's a OS, then somehow the APIs that exist should let the application express the requirements that it has, whether it be the deadlines or throughput or stuff like that. Or alternatively, there might be some global constraints, like I'm designing a speech processing system. I want to make sure that it meets my acoustic sampling rate. So that might be an implied constraint. But there has to be some way of this thing to be known. Then the third component would be the actual optimizer. That is some sort of a decision process which is going to make use of some optimization algorithm with the goal that I achieve whatever I've set out to be, power level or battery lifetime or stuff like that. So that's really where kind of the intelligence lies. And then so those are three things. So let's look at the power model. So we saw power model in a very low level sense earlier on, which is we talked about that how digital hardware can be modeled in terms of those different components and displays and stuff like that. Now, when you kind of pull all of this in together, then in some senses your system would be made up of a bunch of subsystems, and each subsystem you can think in terms of different power states it could be in. So a radio could be transmitting, receiving, idle, off, CPU, same story, disk, same story, and so on and so forth. Yeah.
Is a power watchdog kind of doing something like is that its core function within a system typically, like to analyze the power consumption from different portions of the system and like do.
Actually, I'm not sure specifically what you're referring with power watchdog.
Okay, I mean, I guess I was looking up before in embedded system typical components and different things that exist, and power watchdog came up as one of the standard components, and I think it had something to do with it was sort of a fallback mechanism if a certain part of the system was consuming too much power, then take some action against it or shut it off or do something similar to that. Is that?
It might be something specific with. I mean, I'm not aware of power watchdog as a generic mechanism, so it might be with something specific that you were reading about.
Okay,
So if you send me a link, I'll kind of
okay.
yeah. Um, but from the name you're saying, it sounds like it's if something is consuming too much power or something, then I'm going to take some action. Sounds something like that. So when it comes to modeling in an abstract manner the overall state, then a very common approach that people have used in the literature is to really think of subsystems and I guess the whole system eventually in terms of kind of a state diagram of sorts. And in the state diagram, the different states represent distinct distinct states corresponding to distinct functionality, performance, and power. And then there are transitions between them, and the transitions are annotated with how much time they take, and during that time, how much is the power consumption. So, for example, top right, you see state diagram of a hard drive, and very sort of crudely, the hard drive consists of three states. It's working, it's idle, and it's sleep. Working means so hard drives, as you know, a platter and it's spinning. There's a head, then you read write and all. So it's working, and there are kind of IOs being done and all. Then it is idle. So essentially, what happens is a request arrives from the operating system to the hard drive. The head moves, does the active reading. Once the request is finished, it goes back to this idle state where no active reading is happening. Your head is kind of still and waiting for the next request. In case of idle, the disk is spinning still. And then finally, at some stage, the controller in the hard drive may decide, there's no further requests coming for a while. I'm wasting too much time spinning the drive, so it brings it down. And you kind of see a setting, at least in Mac OS X, for example, there's a setting saying spin the disk down to the extent you can. Okay, so that's the stop spinning part, and there you kind of go in. Now, this kind of power management, there are variety of reasons which affect a decision to go to sleep. One has nothing to do with power; it has to do with reliability. If you shut things down on off too much, they do stress the system, and therefore they reduce the lifetime. Ignoring that aside, if you see out here, you would notice that spinning up is pretty costly. Okay, now this is admittedly a older hard drive, but you will see it's obviously you see different numbers, but spinning up is pretty costly in terms of time it takes, and also therefore during that time the energy. So what happens is when it's spinning up, it starts out working against the static friction. So that's where you see the peak current of a drive. Peak current of the drive is not when it has reached the stable spinning state, but rather when it is spinning up, when it's accelerating up to that. So, and then otherwise you would see numbers which correspond to power, and I guess working is kind of dumped into reading and writing into the same category, but you might imagine that it might be different in some drives also. Lower right, you have something for a CPU. This is a very simple CPU. Modern CPUs are a lot more complicated in terms of states that you would see. So in this particular case, again, the CPU has a run state, an idle state, and a sleep state. Again, you have transition times and power numbers which correspond to these things. This was an early version of an ARM processor from almost a dozen years ago. Modern processors, if you look, there are many run states. They correspond to different frequencies and depending upon the voltage, therefore different power. And likewise, there are different degrees of idleness. For example, I'm idle, but is the clock still up? am I still listening to the interrupt, those kind of things, versus idle, where increasingly things processor is idle but the cache is maintained hot, versus processor is idle and the cache is powered down. So you can imagine that kind of in actuality there'll be with modern processors you don't have a three-state diagram, you have kind of a much more complicated thing that will happen. So so power managed. So somehow, so you need to have um, you need one needs to have this kind of a model of the system. The precise numbers within them are going to come from those earlier lower level models that we kind of talked about. Now, either that or from measurement exercises. But at the end of the day, what happens is that components which have to expose to the power manager in the system what their states are. That is, what are the different states in which they can be put for power reduction. So what are their power states and what are their performance states. And in the PC world, the BIOSes and all, they kind of use some very specific jargon to describe these kind of states, so like D state and P state and all of this is used by the firmware to then, or the hardware abstraction layer to kind of manage the resources on the main board of the computer. So anyway, so the three main kind of characteristics, again, what's happening in the state in terms of power consumption, and what's happening in terms of time and power in terms of transition, which goes between the two. Then the second point which I said was that somehow we need to know the constraints. Are the tasks happy? Is the workload meeting its requirements? So this can be a tricky one. So the intuition, your immediate reaction would be, OS needs to know something, requirements of the application. Let me ask all the applications to give me their requirements. A couple of problems with it. Firstly, since a lot of legacy applications already exist, they were never written with the world of power management in mind, so they don't do it, and we certainly can't expect all those applications to be rewritten. And the second issue is that even if you ask for it, people get it wrong. It's very hard for application developers to meaningfully convey what performance level that they need and all. So you haven't outside the specialized world of real-time systems, we haven't really seen emergence of APIs where applications convey their performance requirements to the OS. You don't see that in, let's say, when you're writing a program on Linux or Windows or stuff like that. So approaches that have emerged for it come at it differently. You didn't tell me, but I'll observe you and see what you need. Okay, so what I mean by that is that by the OS's observation of applications characteristics over time, you can begin to say something about what application needs. So if, for example, I have an application which every 1 second wakes up, reads the sensor and processes it, after the OS has observed it for a while, it now learned what the application looks like and then uses that as the requirement. So first approach is then the OS observes the degree to which resources are being used and then use that to essentially create a model of the application and use that to predict what may happen in the future. So pretty interesting in a way, because now you basically can work with any application as long as it's not doing some sort of a utterly random chaotic behavior. Second one is that applications, this is the one which I kind of dismissed, which is applications somehow convey this thing, okay, and that means that you do need to provide the APIs and all, but the harder part is applications somehow need to assess their requirements, and that's usually the harder part. Application developers tend not to have that, and this is also complicated by the fact that in many cases, you're moving from platform to platform. So, for example, if the application is running on a faster CPU, it may need less of a CPU time than if it's running on a slower CPU. So, it's very hard for applications to describe how much CPU time they need, and all in a manner where which scales across the heterogeneous platforms that they may run on. But the advantage out here is that essentially application knows best, and therefore OS can be a lot more aggressive about it. There exist, I guess, these two camps in a way represent. I mean, I partly see them play out. What's the responsibility of the application versus what's the responsibility of the or how smart the OS is? I see it play out actually just between iOS and Android. So in iOS, Apple's philosophy has been to not burden the app to the extent possible, and then have the OS sort of be smart about these things, whereas Android went the other direction and really gives some finer control to the applications, including the concept of something called power lock. So you can basically put, you can tell the OS on that I'm taking, for example, I need the screen. Don't lock it. Don't shut it down. So you can at some granularity can begin to place, I think a wake lock as they call it, that keep this thing up. Yeah.
Is this why the Facebook performance on Android is so terrible compared to iPhone?
I don't know. But what did happen? Actually, it may have something to do with. Okay, so there was a series of papers which showed that many applications on Android do not correctly use the so-called wake lock facility. So even when they don't need a resource to be up, they leave it up by mistake, and therefore the overall system performance does take a hit. But having said that, Facebook, I do recall on iOS, had some issues on this front also, which is it was not it was consuming excessive energy on some front. So I think power management, if the application is involved, then essentially application also has the responsibility to behave correctly. So the tension that you face is that the any power management has to be done by the OS, because I cannot let a single application kind of willy-nilly shut down resources and all. So OS has to do it, but the knowledge that is necessary is really with the application, and many a times the application doesn't know it that well. Okay, so that tension which comes up. One of the ongoing debate always has been that when it comes to power management, who's the responsible party? Where is it best done? Is it application? Is it OS? Is it compiler? Is it hardware? And all of these choices have tensions. Hardware certainly has advantage, sitting at the lowest level. It can shut things down and all very easily, but it has absolutely no clue what the software wants, unless the software tells it, or unless it somehow automatically figures it out. OS can certainly do the management, but again, it lacks the application knowledge. Applications, even if applications have the knowledge in many cases, so they could be smart about it, but they are not the only application. So application 1 doesn't really know what application 2 wants, and now you end up into a hairy coordination problem. So where to do this stuff becomes kind of a source of So in a sense, power management now boils down to that I need to tweak the different knobs that the hardware is providing in a manner which is energy optimal with respect to some objective, while keeping the applications happy. And all these parties in general, will be involved in this process, namely hardware will do some stuff, OS will do some stuff, and applications will do some things. I think currently, dominantly, it's either the hardware or the OS. So the hardware comes into play in the following sense, that generally the hardware defers to the operating system, except if the system starts going into a dangerous territory. That is, if the processor is overheating or stuff like that. So you would see these kind of things where suddenly your phone is overheating and then kind of just the whole thing dies, and that's basically thermal regulators in the hardware kicking in. making sure that you're not getting into dangerous territory. Other than that, you defer it to the OS slash BIOS firmware. And applications, I guess, applications currently by and large provide hints. There have been cases where sort of applications may be given direct control, but then there would be kind of very specialized systems where not in a more general purpose setting. So so then the question, so if the OS is carrying bulk of the weight, it really boils down to the scheduler of the OS. That is, scheduler in the OS traditionally makes a decision solely about when to run a task in a multi-core setting, where to run the task. But now you can imagine from a power management setting, it also has the additional responsibility of controlling these knobs at the hardware level. It can shut down pieces of the hardware, it can change the speed setting. In effect, it has to move the hardware or subsystems from across those states. It has to tell the disk, now you shut down or now you wake up or stuff like that. Again, the reality is somewhat more complicated. So taking the disk example, the disk shutdown is certainly triggered by the OS, but the controller of the disk, which is a low-level processor, also plays a role. So reality is more complicated, but the first order OS is affecting this stuff. So power management then boils down to what policy the OS is using. So in addition to scheduling, it has this power management policy. Now, this is where things get insanely complicated. So sort of essentially you have informed heuristics or of various forms. So one thing that's starting out, and which was kind of essentially people started out with early on and then realized that this is not the best thing you can do. So we moved to more complicated things. But again, perhaps we are back to an era where this works well. And that is basically saying maximum performance is also the greenest performance. What it is saying is that run as rapidly as you can. So any optimization which makes your application run quickly is also the optimization which makes the overall system green, because I can then shut the system down so the system is maximally asleep. As we saw from the hardware models, this is not necessarily the best strategy if depending upon the balance between the leakage and the dynamic power consumption. So, but anyway, this is a race to sleep or sprint to the finish line kind of a strategy. So this holds true when the power is dominated by the switching type power consumption and not the leakage power consumption. The other one is playing smarts. So you basically adjust the hardware performance dynamically, always constantly tweaking the different knobs that you have. And the knobs that you have are pretty rich. So we already saw supply voltage and frequency. You also have a knob related to something called substrate voltage, which affects the threshold. You also have other knobs. You can decide whether to run on a big processor or a small processor. Those kind of things, that how many processor cores are up and running. Those kind of things you could you could. So adjust hardware performance level dynamically. That's the second one. And let's see. Yeah, I'm going to skip that one. Okay, so when this whole power management stuff started and all, so very soon kind of it became evident that the BIOSes or the firmware of the computers would have to provide support for it. So Intel, which effectively owns the platform, kind of went through a series of sort of standards to make the to provide a standard way for operating systems to do power management on PC platforms. So what emerged out of that is something called ACPI, so Advanced Configuration and Power Interface. It's basically a hard abstraction to the hardware that the firmware provides, so that any ACPI aware operating system can use that. So the power manager in the OS sees the hardware, different hardware platforms in a through a common lens. Okay, as that's their hardware abstraction layer basically. So early on, back in 90s, there were some first cut attempts and all, and then eventually kind of things settled around ACPI. So what essentially it does is it lets the OS figure out what are the different subsystems, what are their run states and power states, and it lets them control those, migrate, like telling the disk shut down, stuff like that, in a standard manner. So now OSs can target this ACPI set of calls and work with that. So what it does is then it defines a whole bunch of power states. That's one of the things it does, and it does so at the overall level for processors as well as for various devices. So when you're bored have a device, it basically kind of tells the BIOS, here I am, and by the way, these are the relevant states that I have. So there's kind of some lower level dialogue that happens. Um, so there's a whole bunch of sort of nitty-gritty which happens at the state. The key thing to keep in mind is ACPI itself does not do any power management. That smart is still in the operating system. What ACPI is doing is basically giving a standard way that the hardware and its power management related capabilities are made visible for the operating system to exploit, or even make it operating system to make it visible to the application. There were a lot of concerns about this thing. I mean, a lot of issues around that. I have some quote from Linus Torvald on kind of ACPI was not always not viewed positively. It's also viewed as a security risk, because the way ACPI works is that it actually makes use of bytecode programs which are then run. So there are all sorts of security issues that emerge from that choice also. But leaving those aside, just a glimpse into what kind of states and all that exist in these systems, and then everything else is then built on top of that. So at the highest level, there is a concept of global states. And there is a global state 0, which basically says system is working. Then you have a global state 1, which is saying that things are asleep, but there are further distinctions within that, S1 through S4, which is basically corresponding to deeper and deeper notions of state. So S1 says all processor caches are flushed, CPU has stopped executing instructions, power to the CPU and RAM is maintained, devices, peripherals that do not indicate that they must remain on may be powered down. So this is kind of some state, and on your particularly DRAM state is maintained. State 2, CPU is powered off. So state 1 was CPU had stopped executing the instruction, but it was still powered on. In state 2, it's powered off. State 3 is RAM is powered on, but otherwise things have gone into standby and all. And state 4 is suspend to disk, where basically the main memory content has been saved onto some sort of persistent thing and then maintained there. The disk or flash memory or whatever. Some of these things are evolving. So like, for example, now we are seeing emergence of memories where you can maintain state for a really long time. So the final state, the hibernation, may not happen. So that you do by lowering the voltage to the DRAM and putting them into an ultra low power state where they can last for many days or even like a couple of weeks. So you can maintain things that way also. Then you have state G2. It's G2 and D3, but basically the idea out here is that computer is in a state where it can wake up from an input. So it's kind of asleep, but I press a button or a packet comes over the network, then it can wake up. Okay, so you see that a lot now, even over wireless. But early states, what used to be was your computer is hooked up to an Ethernet, and there would be the Ethernet chip would listen for a specific packet, and when that packet would arrive, it will wake up the computer. So essentially, arrival of a packet matching a certain bit pattern resulted in a interrupt being generated, which woke up the rest of the machine. There is an analogous thing on wireless side, which is the wireless chipset remains up, waits for a particular wake up packet, and wakes the whole system up. G3, mechanical off. So in this particular case, if there is a switch on the computer, it has been put into an off state. Now, even when you do that, there is still some stuff which remains off up in a typical desktop, which is to maintain the real-time power, real-time clock as it is called. And if you unplug the power cord, then there is a battery on your motherboard which maintains that state, which is how when it comes up, it still has a reasonable notion of time. And then there's some support for legacy state. So at the highest level, this is the view of the system that exists. Okay, so running kind of these different notions of sleep, and then the ability to wake up, otherwise off, and then finally kind of really can't be woken up without some manual intervention. So this is kind of a summarization of the capabilities that exist at the level of this global state, and then the sleep substates that sort of happen. And main thing is really what needs to be done. Does the OS need to be restarted? What kind of context is maintained? And all of this kind of ends up dictating your power management strategy. So that's for the overall computer. Then for each peripheral device, like your hard drive, your radio, stuff like that, there's a similar set of states that would exist. So for each device in the system, there are different states which are defined, and so fully on through kind of intermediate states and then finally off. And kind of again, the idea is that there's a trade-off between power consumption, the context retained, and how much time would it take to revive the device. So your decision to shut down a device in part would depend upon when do you expect next to use it, and sort of incorporate, the OS has to kind of incorporate that in its decision making. And then finally, the richest set of states come from the CPU, sort of justifiably so, because it's the most complicated piece which is out there. So within the CPU, again, there are a whole bunch of states of different types. So C0 is the operating state, and then you have states like halt and stop the clock and so on and so forth. Similar kind of thing. This is very Intel biased, but you would see similar things in other processors. So that's a high level bit of CPUs. And then there is something called performance states, which correspond to different frequency performance level. Performance states are both for processor and actually also for the devices, which are basically saying maximum power and frequency, and then states which are increasingly less performance and presumably less power as well, and so on and so forth. So in Intel, P states were called as speed step. Other manufacturers may have similar things. It does require support from the board because the voltage needs to be changed. So frequency can be changed within the processor, but for voltage to be changed, you do need additional system support. But at the end of the day, your devices and CPU and the processor are going to have a bunch of performance states. So global system kind of these states for CPU and devices, you have a bunch of these sleep and work states, and then within the work state, you have these performance states. And what the OS has to do is to kind of manage each one of these as part of its power management strategy. So let's see what else. Yeah. So overall state diagram of the system kind of looks something kind of a hierarchy of these states within components. Within components, I have state diagram, and all of this thing has to be characterized. And when you plug in a new device or whatever, somehow the BIOS has to learn about it and be aware of that. So now, once your system provides this kind of, if it's using ACPI, provides this kind of abstraction, then the power management module within the system is going to implement some strategy. And the race to idle or race to sleep strategy is work in P0, which is the highest performance state, and then revert to the slowest state, Pn. Pn basically means the slowest state in which my device or processor is still working, or even go into one of the sleep states. And then either arrange for a wake up based upon timer or based upon some external interrupt or some other criteria. One of the things that happened is this is maybe around 10 years ago or so, that the Linux first and then other operating systems moved to what is called as a tickless model. So let me explain that a bit. The way operating systems operate, these general purpose ones, they have a clock tick, and every so often, something called a jiffy in Linux, essentially a clock interrupt comes, wakes. So the interrupt handler in the operating system handles that, and then if nothing to do, goes back to sleep. Typically, when it wakes up, it says, "Hey, are there events waiting for me that need to be handled? Has an event happened? Maybe a timer was scheduled," and then go back to sleep. What happens in this case is that my system is waking up every 10 millisecond, 15 millisecond or so, which is essentially prevents long sleep. We already saw that transition times between states are of that order. So what tickless does is it basically says, if I have nothing to do, if I know that there are no timers that will be there because I know the state of timers, why bother waking up? So essentially you'll see a whole bunch of ticks skipped, and you immediately rush, and then you go to the next time an event is actually going to happen. So you delay, so you try to avoid unnecessary ticks, and combined with this thing is another aspect that brings out is that if I can delay a task, let's delay the task. So for example, those of you who are in my 202A class, if you recall, when it came to real-time scheduling, the way our schedulers always worked was that if the CPU is available and the task is ready to run, then I'm going to run it. Okay, and that's how schedulers. This is called work conserving scheduling. It's basically saying that I will never knowingly not use a CPU if the CPU was available or the resource was available and the task was ready. There is something called non-work conserving one, and they basically say that, I know something about the future a little bit, I can speculate. I may be better off not using it right now, maybe I'll use it later. And the intuition out here would be, by delaying things as much as possible, I can elongate my sleep period and therefore gain more out of the sleep. So in this model, what happens is that if I have a timer, maybe, so let's say process A says, timer wake up at 5 p.m. Process 2 says, timer wake up at 5 p.m. plus 20 millisecond. So instead of waking up at 5 p.m., handling it, going back to sleep, waking up again at 5 p.m. 20 millisecond, what if we were to shift the first timer or move up the first timer, whatever, maximize, align them. And so you delay the timers and you align the timers if the application permits, and then you have a big win there because you can maximize the sleep times. It obviously raises concerns that the timing to the application may not be precise. But if you think about it, in any case, in general purpose computers, any case, you don't know things to that level of precision. Okay, when you ask for sleep for 5 seconds, by the time your application actually runs, there are inevitable delays through system calls and all. So 5 seconds is never 5 seconds precisely. Anyway, so both Windows and Macs, and I don't know about Linux on this regard, but possibly it does too. They take fair bit of liberties with the timers now. So original application schedule timers might be at random times, but they kind of align them so that the system is woken up, and then when it wakes up, it handles a whole bunch of events and then goes back to sleep. So between these two things, tickless and this messing with the timer, a lot of lot of improvements has resulted in a lot of improvements that would otherwise not be possible. So uh, we'll see some examples later on when we go into a bit more into the guts, but at a high level, then the scheduler in the OS is kind of playing these games. Any of you have experience with power management within the OS at this level? I'm just curious. I know your group does a lot of work, Kaiser's group. No, you don't. Okay. So these policies that I talked about, governing things and all, in Linux there is a very stylized framework called govern. Yeah, wait.
I'm just curious, in order to do this kind of power management, it seems like really critical, so it should be operating on the kernel, right?
Oh, it is inside the kernel.
It's in the kernel,
Mm-hmm.
and it requires support from the hardware. There is like.
So ACPI is again software. It is what you call as BIOS or firmware. Okay, so ACPI hides the hardware from the operating system. So the operating system, when it is running on a board, it will make calls to the firmware. So when the operating system needs to shut down the disk or find out what power states the disk has, it makes these well-defined ACPI calls, which is another lower layer of software. And that lower layer of software is written by the board manufacturer. Okay, and whatever that manufacturer puts in the necessary code to actually do the hardware shutdown and all. And then finally, of course, the hardware designer has to provide the ability to shut down and all, right? I mean, so that the fact that all those states exist is because the hardware designer chose to put it out there, or perhaps the board designer, either the chip designer or the board designer has to provide support for that. Okay, but the intelligence part, the control algorithm, resides in the OS, and in case of Linux, they're called as governors. Okay, so there's a framework where essentially it's a very modular framework, so you can put different power management strategies, and they're very tightly coupled with the scheduling strategy. Okay, because once you do this power management, then your schedule is also going to be impacted. If I shut something down, then it's going to impact the schedule. So there's a very choreographed set of operations taking place across these three different things: hardware, ACPI, it is kind of essentially passing through, helping it to mediate, and the operating system.
So for the different hardware, it should be like maybe different strategy to operating on the ACPI, and how the software will, like you say, the algorithm is like is in the software, but how the software adjusts its strategy depends on the hardware. There's so many kind of the hardware over there, and with different manufacturer, different configurations.
No, so what ACPI is doing is precisely hiding those. It basically says that to keep life simple, we will expose hardware capabilities only through the abstraction of those states. So even if the hardware has some additional capabilities, if ACPI cannot express it, then the OS will not be able to use it. Okay, so what happens in this thing, the way this world operates it, Intel decides this layer.
Okay.
Or Intel and Microsoft in the older days, and I guess nowadays perhaps a richer set of players. And then the OS exploits it, and hardware vendors basically support it. So, and the board manufacturers kind of write the ACPI, the firmware. Okay. So any advances in hardware have to wait for Intel to formally support it. Basically, I guess that's my answer. Okay. I guess things are different on the ARM side, relatively speaking, is a more free-form world. So there you see embedded systems and all more directly adopting stuff. I don't think to the first order there is a similar ACPI kind of thing when it comes to mobile devices, but it's kind of dominant. The world of mobile devices is extremely different than the rest of electronics. So like let's say you are designing something around Intel processors. You can go to Intel website, you can look at the processor, you can find the data sheet, you can download it, you have the pinouts and everything, what they do, timing diagrams, you're done. Try getting it from Qualcomm. You go to their website, you will see high-level description, we have Snapdragon 835, so many cores and all, but getting the data sheet, they never hand it out. It's only available to handset vendors. So, uh, so, so, so a lot of details which are, it's quite possible that on the Snapdragon side of the world, there are similar standards that essentially Qualcomm enforces for any handset vendor, but there is no easy way to kind of learn about them. And it's the same thing is true for other companies in that field. Broadcom, same story. Marvell, same story. I don't know about like MediaTek, which is a Taiwanese company, which is another big manufacturer. Samsung, same thing. Their Exynos processor, you can't really find any information really. So these are kind of essentially when it comes to their power management capabilities and all, you kind of know at a high level what they're doing, but you can't really sort of. I cannot teach around them. I guess is what I'm trying to say. Whereas the Intel world is really just utterly transparent and open. And Texas Instruments, that's the other company which kind of just puts everything out there. So hardware advances, unfortunately, will not make through in this case immediately. Yeah, ACPI has to kind of support them. Okay, so here what I'm showing is kind of some a modem hooked up to Intel chipset. So there is some sort of a UART, there's a modem controller, there's a phone interface. This is obviously an old example, but that's what the ACPI standards had. So in just to illustrate, what might happen in this case is that there might be a bunch of device states, device in this case being a modem. So it could be, for example, in terms of what are the capabilities, like is the modem on or off, is it on hook, off hook, stuff like that. Then there is a variety of power policies in terms of transitions which are possible. And then finally, what is the wake policy? So when it comes to power management, really at a very high level, you really have, you're trying to make rules about when would you transition the device or the processor or the system across those different possible transitions. And in a very crude sense, you can say there are two separate set of decisions. When will I put things to sleep, and when or shut down, and when will I wake them up? Okay, so if you were to think of a very simplified view, on off, then my shutdown policy is simply when should I turn it off and when should I turn it on. Now, the simplest one you could say, if I see I have nothing to do, I will turn it off. And the moment I have something to do, I will turn it on. The problem obviously with that is that turning on and off take time, and so that has implications. So the actual policies then have to account for those. But basically, kind of the policies have to kind of support all of this. Another point I wanted to make was that in complicated systems, there might be power management going on in multiple places. So there is OS doing it on the CPU, but it's also possible that the controller on your external USB drive is doing its own power management, because you often see that, right? I mean, the disk spins down and all, and that's happening because of some local decision making. Or likewise, earlier on I said for thermal reasons, the hardware inside the Intel chip might disobey the operating system and shut the processor down because it was heating up. So there's always kind of that self-preservation layer or an independent distributed control which is happening separately. So one has to sort of keep that in mind, which happens in a real system. ACPI, when it had first come out, was the era of desktops. So battery support kind of tagged along a little bit later. So ACPI was in 90s and all, and at that time laptops were just kind of coming out. So battery support came kind of later there. But now ACPI provides support for querying things about the battery. So like what capacity does the battery have, the charge level, rate of discharge, stuff like that. All that stuff I was talking about in the previous slide set, state of health, state of charge and all, they're exposed through the ACPI. Is the battery inserted, removed, has it stopped charging, discharging, battery levels, stuff like that. So again, this is the Intel side of the world. I don't know what happens on, even though Intel, this is Intel Windows side of the world. So I don't know what happens on the Macs, for example. I don't think they use ACPI because they use a different firmware altogether. Anyone knows on the Macs? No? Okay. And certainly on the embedded side, it's freeform. So
I think I think one of the examples that you showed, the earlier pictures where you showed the SA110 processor, that was an Intel.
SA110 was so
Intel
SA1
ARM, right? It's an Intel,
Intel
ARM,
ARM, which is no longer made. Okay, so
right. So
and
they still use the Intel power management.
no. So there's a long story behind SA110. So SA110 was made by a company called DEC.
Yeah, these.
Okay, DC. And Intel had bought that part of DEC. Okay, and Intel started making ARM processors. And this was an era where Intel was trying to get into IoT. This was their first attempt.
And then later they sell it to Marvell.
And they sold it to Marvell, correct. And then Intel pulled out of it. And then now Intel has again gotten back into embedded space through Atom, and then they have these processors called Quark. Over the past few years, that's the re-entry of Intel. So Intel had a tortuous history. They had built up a robotics group, they had built up a sensor network group and stuff like that. And around 2007 and 8, they kind of shut them down.
So you were saying even though Marvell bought that division of Intel, they did not use their power management ideology.
ACPI was always on the i86 processors. So it never. I think the embedded world just remained way too fragmented in all this regard. So, but I'm pretty confident that just for the sanity of system designers, vendors like Qualcomm must be using something, and likewise, I know Apple has a very systematic power management stuff. I just don't know the details. And in fact, power management is often done. So I mentioned that operating system does it. Okay, but the problem is that some of the power management activities have to take place while the main processor is shut. So there's a coprocessor to do that. So there's a power management chip, or on the main processor chip there is a power management board which is kept up and which does this stuff. And on Snapdragon, as I understand, it is actually done on a Cortex processor. So Cortex M3 or M0. So that's what apparently Snapdragon uses, a tiny power management processor which does that. Some of you might have deeper insights into that, but these, like you learn about these tidbits and all from conversation, but these are not like data. Like I said, there are no data sheets and all documenting these things. So, they're probably, for all I know, proprietary information. So in any case, so there are power management modules or things which are usually there. Just today I was reading an article that Apple, it went along the line that Apple is going to be putting in the next generation computers ARM-based processor or T something, which is going to be responsible for power management and a bunch of other things now that increasingly happen while the rest of the system is shut down. Because what's beginning to happen is that when the system is shut, I guess there is a new type of power state which is emerging now, and it is the following: system is not doing anything, but it can hear the user, it can interact with the user. So this is the example of like Hey Siri or whatever, gestures or stuff like that. This didn't exist in the older situations, or even other things like my computer is asleep and then the fingerprint sensor that my laptop has. These the things that we expect the platform to do while asleep have gone up, and which is why this kind of interesting new class of processor which has begun to emerge. Motion related stuff is another one, right? I mean, motion processor on the iPhones is an example of that. So we've kind of, I think this picture that I presented obviously kind of doesn't capture these newer things that are happening. Okay, so let's see. So, the other another thing is that very closely tied with the whole issue of power is the whole issue of thermal management also. So at the lowest level, at the chip level, there are always thermal protection mechanisms and stuff like that that will overrule anything the OS is saying to make sure that the chip doesn't heat up and burn itself out. But even beyond that, the system would have things like cooling zones, fans, they need to be turned on off, fan speeds are adaptively controlled. All of this also happens through the same BIOS interface. So there are controls for this thing. So usually it's very common in the low end PCs and all, and there will be a single sort of thermal zone, and then there will be some sensors and a fan, and you're going to control that, and that's how it works. But the moment you move up a little bit higher up, blade computers, big towers, and all, you may have multiple fans, and the speed may be adapted partly because of noise reason also. So all of so all of that is managed again through kind of the same framework. There are sensors, there are cooling mechanisms, and you kind of coordinate them together. So what I've described thus far is kind of the enabling layer, right? I mean, this is how a power management scheme on top of the hardware and this ACPI and all can kind of work. The next question which comes up is, what should this scheme do? I gave you some sense of policies, what the policies have to do, but we spend a bit of a time going through at least the first generation of these policies that has come up. So intuitively, you can think of your system as some sort of a service provider. And then there is a service requester, which are your applications, user, external world. And it's sending requests. And these requests need to be serviced, so you can think of them as some sort of a queue perhaps. And then your power manager, DPM, power manager, sort of sitting there, and it's kind of observing what the system is doing, observing what the application is doing, and then it basically observing what the status of the queue is, and then it's essentially in a very simple system, just sending on-off command to the queue. Okay, so this is a very simple scenario you might imagine. I have a server serving a queue, and I have to issue on-off command to the server so that we can minimize power. And now you can think of in this setting different type of constraints might be present. Like for example, my queue is finite sized, so I don't want it to overflow. I don't want the time to service to exceed certain things. Okay, all those, I should be able to sustain a particular average rate of arrival of the request. I may have turning on and off may take certain amount of time, so the server may be unavailable for certain duration if I duty cycle it too much. So you can begin to model this problem in a somewhat abstracted manner so that you can reason about it in some way. So that's a high level view, and then each one of these the component inside the service provider, you can think of them in terms of the states and all that they provide. So when is something like this going to be useful? So if in a very simple scenario, I think of the system that I am seeking to power manage as having two states, and then I can turn it on or off. And I have applications which are basically moving between two possibilities. So application is actively needs the resource, and then at some stage, application is done with the current event, handle the current event, and is waiting for the next event. So a lot of things are like that. They wait for an event, the event handler runs, we go back, wait for the next event. So you can model these things in these terms, and now you can say that if my system, the underlying hardware, ideally what I would like is when the application has nothing to do, the system is in the off state, and when the event handler is actively running, we are in the on state. And then I do this transition back and forth, and the transition is going to cost us something. The transition takes some, during the transition we consume some power, and it takes certain time. So this energy, PTR, P times T, P sub 6 TR, T times TR, represents the energy cost of doing a state transition. So excessive power management is going to result in some impact on my energy consumption. If I'm wrong, I can also miss a deadline. One of the issue with the strategy of I will wake up when the event comes is that my latency has increased, right? Previously, if my system was up, when the event comes, I can immediately handle it. Whereas if I was asleep, when the event comes, I have to first wake the system up and so pay energy and time for doing that. So if transition time was 0 and power consumption doesn't matter in that case, then the policy is trivial. Stop using the system when it is, or whatever, stop a component when it is not needed and wake it up when the moment it is needed. And since time taken is 0, so there is no overhead, no excess energy. But no real system is like that. So in reality, transition time is not 0, and during transition, power consumption is not 0. So then basically, intuitively, your strategy will have to be shut down when the application is going to remain, application is not going to need the resource again for a long enough time. Because if it happens that I decide to shut down and the application very soon after decides to need that, hey, I need the resource, then essentially I'm going to pay a round trip energy cost and a latency cost, and I may be worse off. Okay, so I cannot, in that case, be very aggressive about shutting things down. So shut down only when it is going to be worthwhile. And the problem is that I typically, unless in some settings, applications workload temporal profile may be very deterministic, but as you can imagine, in most cases, I really don't know when the application will precisely need me. I can make guesses about it, I can make predictions about it, but I certainly cannot be very deterministic, be confident about that. So our problem then basically becomes that in the face of this kind of a situation, how can I make a more informed decision about when to shut down? Should I shut down? And likewise, I have to make the decision about when to wake up. If I wait until the event comes, then I have to take up latency. So alternative might be I somehow try to predict. I basically say, the application comes every 5 seconds, so let me wake up a little bit before. So I hide the latency so that by the time application needs me, I'm up and running. So it's a type of an online problem. Our problem would be trivial if you were to give me the trace up front. That application will come at 5 p.m. and need you for 10 seconds, and then it will come at 5:15 and need you for 5 seconds, and so forth. If I knew that, then it's an offline problem, and essentially have a view for the entire time, and I can basically run some sort of a optimization of that. But this problem is an example of what are called as online problems. That is, I have to make a decision without knowing the future, and in the face of that, really I can at best try to make guesses about the future based upon some model of what the application behaves like. So this is an further example of how sort of some of those cases. I think I can see you've seen these pictures before. Okay, so the problems in shutdown then basically kind of be listed as following. The first is cost of restarting. There is a latency versus power trade-off. So I can, sorry, the latency and power. So when I restart, I have to, it may take time to come back up, like a hard drive spinning back up, and or restoring the CPU state, might even involve the OS being rebooted and all, and the power consumption. When to shut down? So you can imagine various policies. I somehow know about the future. I know that the application is going to come sufficiently later in time, and therefore I shut down. Very common policy is idle time threshold. Shut down if I have already been idle long enough. Okay, so you see these things often in, at least in earlier days, both Windows and Mac had these kind of sliders where you can say if I have been idle for 15 minutes or whatever, then shut it down. I think Mac still has it for the screen if you are idle after like shut down immediately or do it after 10 minutes or 15 minutes and whatnot. This kind of a threshold policy, intuitively, what is it saying? I mean, remember, our goal is I want to shut down if it's going to, if the application is not going to need me for a sufficient amount of time. So a policy like this, which is saying you have been idle enough for a threshold time, let's shut it down. What is it saying about the application? Like if I'm basically making a prediction that okay, I've been idle for a certain time and therefore it's worthwhile shutting down. So what is it saying about the application characteristic? Right, I mean we're making a prediction. This is guiding something, right? But,
Just like desktop computer.
No. I'm basically, I mean,
Using the previous data to predict.
so the assertion I'm making is that my decision is, no, it could be on any right? I mean, basically, so the moment I became idle, I had a decision to make: should I shut down or not? And one way of thinking about it is, I'm basically saying that will the application next need me sufficiently far in the future? Okay. This policy, which we see very commonly, is basically saying, let's wait for delta time, and if during that delta time the application does not need you, let's shut down. Right? That's what this policy is saying. My question for you is, what is it saying about the application behavior now, right? I mean, why am I saying wait delta time and now shut down? Why not immediately shut down? What does delta time buy me?
The least arrival time between two events is delta t.
Well, if it was delta t, then that's a bad strategy because then application will come immediately.
Then that's the least time. You have, that's the maximum time.
Make up your mind.
That's the maximum time you have to wait.
If it's a maximum time, then it's an awful strategy, right? I mean, if the maximum inter-arrival time is delta t, then obviously the strategy is an absolutely awful one, right? So it can't be that. Average time?
But it doesn't even within the delta t, then the wake up time might take more power than.
Okay. Think of the time for arrival for the application to be a random variable. Let's call it x. Okay. Then I'm making an assert, and let's say x needs to be larger than a certain amount for it to be worthwhile. Then I'm basically saying that probability x is greater than that sufficient amount time is very high if I know that x is greater than delta, right? I mean, essentially that's what I'm really saying, that if the application, so intuitively this is saying something about either you're going to be shut down for a very short amount of time or sufficiently long period of time. That is, the application has this kind of bimodal characteristic. So application has a lot of tiny periods which are not worthwhile, so let's filter them away. And then what's left over are kind of those things. So either I have gone for lunch and therefore I'm going to be, or it was just like turn to talk to someone and all, and you don't want to do that, right? I mean, that's basically what this policy is saying. That, and I'd always wondered, like, what should I set it to? I mean, almost for me, always it has been that either set it very high because I know I don't want it to shut down on me, right? I mean, there's no other guidance which is given. Now, more importantly, somewhere in this thing, that delta is going to depend upon all these other hardware variables we are talking about, which we never have an insight into. But we'll see that this delta does relate to something called a break-even time, okay, which is a hardware characteristic. But anyway, so this is a very common policy that you encounter, but I think it's a very thoughtlessly designed policy because you really can't, most users can't pick it. Predictive, so I guess what I'm saying is might as well they could have just given us two choices: shut it down immediately or never shut it down. I mean, for all practical purposes, it's kind of between these two. Predictive means that essentially precisely what I was saying, that at the moment the system became idle, I'm going to make a prediction. Is it worthwhile for me to shut down? Which is translates into, is the application not going to need me for a sufficient period of time? And I'm going to keep making this decision. Okay, maybe some additional information came along the way, and then I might change my mind. Okay, but that's in essence what you see. When to wake up, you face similar issues. There's an optimal one. So when to wake up also raises a subtle question as to the unstated thing out here is that I want to wake up in a manner that the application performance is not hurt. So that is, application would not realize that the system was shut down. What that means is that I should wake up sometime before the application arrives, right? That's the only way application latency will not be impacted. So optimal strategy would end up doing that. If the application said it will come at 5, if I know magically that application will come at 15 minutes or 5, and if it takes 1 second to boot the system up, then I will actually wake up at 5:14:59 to start doing it. But again, sort of a oracle view or a God view of the timeline can do it, but you don't know the future. On demand takes a hit on latency, right? I mean, when the event arrives, now I'm waking things up, and that is affecting the real timeliness of your system. It may be okay in some settings, but often not. And I think one of the things that has happened, I think I mentioned this earlier also, that in recent years, a lot of effort has gone into making the reboot process very rapid. I mean, you guys are too young, but if you just roll back like even 5 years or certainly 10 years, you would see that the reboot time of Linux and Macs and Windows used to be insanely long. I mean, you kind of wake up and kind of just, come up. And in many cases, they still are. But with the smartphones and the iPads and all, that has changed. I mean, you press the thing and it's there. I mean, some of it is gimmickry in the sense that what they do is they prioritize things so that the user interface elements are up and running while the rest of the system is still coming up. But a lot of it also was optimizing the boot process or doing things smartly. So when to wake up, so optimal, on demand, and predictive. If I can predict when the application would come, then I can would be the resource. Then I can perform it. So the concept that sort of plays an important role out here is a characteristics of the hardware, which is a break-even point. And the idea is that it is a time duration where if I had stayed up versus if I had shut down and woken up, I break even. Okay, let me describe it again. If I shut down and wake up and have to wake up too quickly, I will be worse off. So break-even point is saying something about that the shutdown, that the application should not arrive too soon. So what's the minimal gap between the next between now and the next arrival of the application, so that it is actually better for me to shut down, because by going to the shutdown state and even paying the additional energy of shutting down and waking up, I will come out ahead because the gap is long enough. So I see it is 5:40, and since that component will take a bit of time to explain, so I'm going to stop now. But intuitively, this is an online decision-making problem that we are facing on this one, and you can imagine a rich suite of strategies. And this is one of the project ideas that thrown around. Well, as you can see, this is where machine learning can help you also, because you're basically making a prediction. You have to make a decision.
So over sort of one of the earlier lectures, you showed us like a slide of where generally in the process like energy can be saved, where energy is consumed. And is this sort of like, I mean, and it obviously matters the choices you make with regard to when you should shut down and wake up, with regard to energy consumption, but how much really is the capability to cut energy with really focusing on optimizing sleep and wake up policy as compared to the overall
So,
process?
So I guess here I'm sort of assuming that none of those other things existed. You're right that there's a coupling and goes to the issue. Maybe shutting, I should not even shut down. I should stretch the application out. When the application arrives, I should run it at a slower frequency or stuff like that, right? I'm basically assuming right now that I have no such flexibility. I can either run full speed or shut down, and when the application comes, it's ready to run. And my goal simply is to avoid keeping the system in this idle state where it's doing nothing and just burning energy. Okay, so it's a simplified view of the system, and I think you would see that. I mean, even this version of the problem is complex enough. If you throw everything else, it just is a horribly messy problem. So you really are into the world of heuristics and all and what works there. Okay, cool. So see you guys on Monday.